Hello again, everyone. I'm Storm Team 9 Chief Meteorologist Jerry Jackson, and this is Weather or Not. The July 4th holiday may be behind us, but we still have a lot of summertime heat left to go. When you think of relief, the first thing that comes to mind is the pool or the beach. But as Olivia Monteleone shows us, sometimes all you really need is a quick, tasty treat.
Ice cream sales reliably increase as temperatures increase until hitting a peak of 65 to 80 degrees. However, the relationship between the weather and ice cream is full of surprises. While sales usually peak on warm or cloudy summer days, interestingly, cold regions often consume the most ice cream year-round than hot regions. The sweet spot when ice cream sales peak is when temperatures range from 65 degrees to 80 degrees. If the weather gets too hot, sales can actually drop. Customers often switch to lighter treats like popsicles, shave ice or ice pops, and cold drinks. Counterintuitively, many colder weather countries consume far more ice cream per person than hot countries. People in cold climates often eat ice cream indoors, in cozy settings or paired with hot desserts like pies and brownies. Hot weather means ice cream melts fast, which leads to sticky and dripping treats. Hot weather also naturally reduces the sensitivity of your taste buds and smell, increasing the desire for cold textures and sweeter, stronger flavors. In winter, you can enjoy your treat slowly without the mess, and it can feel less intense because your body is already acclimated to the chill, and the cold dairy can actually soothe a winter sore throat. One thing that is associated with ice cream is brain freeze. The freezing cold temperature of ice cream can cause a quick stabbing headache. It happens when cold food or drinks rapidly lower the temperature at the roof of your mouth, causing blood vessels to quickly constrict and then dilate, activating the same nerve responsible for processing facial sensations, which your brain misinterprets as a sharp pain in your forehead or temples. In the winter, the difference between the cold air and the ice cream is smaller, making brain freeze less likely. In hot temperatures, eating ice cream actually cools your body slightly. Your body has to use energy to warm the frozen dessert up to your internal body temperature.
The weather doesn't just affect things here on the ground. After all, the atmosphere is three-dimensional. That's why taking to the sky can be critical in understanding how weather systems truly move.
Hail is a form of precipitation consisting of solid ice that forms inside thunderstorm updrafts. Hail can damage aircrafts, homes, and cars, and can be deadly to livestock and people. Hailstones are formed when raindrops are carried upward by thunderstorm updrafts into extremely cold areas of the atmosphere and freeze. Hailstones then grow by colliding with liquid water drops that freeze on the hailstone's surface. If the water freezes instantaneously when colliding with the hailstone, cloudy ice will form as air bubbles will be trapped in the newly formed ice. However, if the water freezes slowly, the air bubbles can escape and the new ice will be clear. Hail falls when the thunderstorm's updraft can no longer support the weight of the hailstone, which can occur if the stone becomes large enough or the updraft weakens. Hailstones can have layers of clear and cloudy ice if the hailstone encounters different temperature and liquid water content conditions in the thunderstorms. The conditions experienced by the hailstone can change as it passes horizontally across or near an updraft. The layers, however, do not occur simply due to the hailstone going through up and down cycles inside a thunderstorm. The wind inside a thunderstorm isn't simply up and down. Horizontal winds exist from either a rotating updraft, like a supercell thunderstorm, or from surrounding environments' horizontal winds. Hailstones also do not grow from being lofted to the top of the thunderstorm. At very high altitudes, the air is cold enough that all liquid water will have frozen into ice, and hailstones need liquid water to grow to an appreciable size. Hail falls when it becomes heavy enough to overcome the strength of the thunderstorm updraft and is pulled towards the earth by gravity. Smaller hailstones can be blown away from the updraft by horizontal winds, so larger hail typically falls closer to the updraft than smaller hail. If winds near the surface are strong enough, hail can fall at an angle or even nearly sideways. Wind-driven hail can tear up siding on houses, break windows or blow into houses, break side windows on cars, and cause severe injury or death to people and animals. The largest hailstone recovered in the U.S. fell in Vivian, South Dakota on June 23, 2010, with a diameter of 8 inches and a circumference of 18.62 inches. It weighed 1 pound, 15 ounces.
Time for a break. 8 questions, 2 minutes. Good luck. Have you ever considered just how much thought goes into a local forecast? It's one thing to record a quick weather observation right now, but it's another thing entirely to figure out what will happen days into the future. It takes science, computers, critical thinking, common sense, and yes, a little bit of luck.
As meteorologists, we look at numerous graphs, charts, models, and other types of data, but one of the most important things we look at is a skew-T log P diagram. These diagrams are used to plot upper air readings, which we call soundings. They plot temperature, dew point, and winds on these specialized charts for further analysis. The data that feeds it comes from radiosondes, which is the device attached to a weather balloon. As the balloon rises, the radiosonde is collecting data and sending it back to the local National Weather Service office. Meteorologists and climate specialists can derive a lot from upper air soundings using skew-T log P diagrams. They may look cluttered at first, so let's talk about the different parts of these diagrams. The first set of lines we'll look at are the temperature lines in degrees Celsius. These lines are also called isotherms. You can clearly see how the lines are slanted. This makes analysis much easier. They are skewed at a 45-degree angle, hence the name skew-T. Next are the pressure lines, or isobars. They are horizontal and decrease logarithmically with increasing heights. This is where we get the log P part of this diagram's name. You may notice that the lines at the bottom are closer together than the ones on top. This is done to represent the fact that the atmosphere's density decreases with increasing elevation. The next set of lines are the dry adiabats. These lines represent the rate at which unsaturated air cools with increasing height. Keep in mind, unsaturated air is air which the relative humidity is less than 100%. The rate of cooling is about 9.8 degrees Celsius per kilometer, or about 5.5 degrees Fahrenheit per 1,000 feet. Next are the moist adiabats. These lines are curved and increase from left to right. They represent the rate at which saturated air cools. As the water vapor condenses back into liquid form, it releases heat, which affects the rate of cooling. Next is the mixing ratio. This is where the mass of water is compared to the mass of dry air. These lines can be used to derive two different mixing ratios, ordinary and saturated. The ordinary mixing ratio can be found at any height by determining where the dew point crosses the mixing ratio line. The saturated mixing ratio can be found where the actual temperature crosses the mixing ratio line. Finally, we have the wind staff. This is where wind barbs are plotted and are used to analyze the differing wind speeds and directions with height. So now you have a better understanding of the different lines on a skew-T log P diagram.
The world of weather is not just confined to the maps you see on television or your computer screen. Weather affects everything around us all the time.
During the hot summer months, something we have to worry about on top of the heat is the humidity. In this segment, let's go over what humidity is and how it can relate to your car's gas tank. Humidity is a measure of water vapor in the air. There are two different ways to describe humidity. The first one is absolute humidity. This is the actual amount of water vapor per unit of air. But the one you're most likely familiar with is relative humidity. This measures the amount of water vapor in the air, but compares it to the atmosphere's available capacity based on the current temperature. In other words, relative humidity is a percentage of how full the air is with water vapor. Not only does the amount of water vapor affect this percentage, but also the air temperature. The warmer the temperature, the more water vapor the air can hold. And as you probably guessed, the cooler the temperature, the less water vapor the air can hold. When the atmosphere can't hold any more water vapor, the air becomes saturated and the relative humidity is 100%. To make it easier to understand, let's use one of my college professor's analogies. Consider the gas tank in your car. For example, let's say you have 10 gallons of fuel in your vehicle, but you have a 20-gallon tank. At this point, your tank is 50% full. But if you were to shrink it to a 15-gallon tank, then 10 gallons of fuel would make it roughly 67% full. And keeping the amount of fuel the same here, shrinking the tank to a 10-gallon capacity would make this tank 100% full. Obviously, if you were to put more fuel in the original 20-gallon tank, then you will also increase the percentage of how full it is. But in the atmosphere, the temperature changes more frequently than the amount of water vapor, therefore the atmosphere's capacity, or tank size if you will, changes. Let's say the temperature during the day is 90 degrees with a 60% humidity, but at night the temperature decreases to 70 degrees. Because the air got cooler, the amount of water vapor it can hold decreases and the relative humidity increases to 90% even though the actual amount of water vapor stayed the same. With this in mind, 100% humidity means the atmosphere cannot hold any more water in the vapor or gas form, so it starts to condense, turning back to a liquid. Picture this as your gas tank overflowing. This explains why we see fog at nighttime and early mornings while the temperatures are cooler. And since the atmosphere's temperature decreases with height, this also explains why clouds form aloft. So the next time you fill up, I bet you'll think about the atmospheric conditions as well.
Sometimes the brightest ideas in weather come in the smaller packages. Our weather kid this week is Joel. He enjoys playing outside but prefers the winter time.
Did you get to have a snowball fight with your brother?
Who won?
It was me.
It was you. You did okay.
He didn't even throw any snowballs at me.
Okay. And if the weather doesn't cooperate, Joel stays occupied inside.
I mostly just play games,
What kind of games do you play?
like Roblox.
Now, Joel isn't just all about playing. He's got some big plans for adulthood.
I want to be a pet doctor.
A pet doctor, so you want to be a vet. What got you interested in that?
But could you get to help pets?
When it was time to talk weather, Joel really seemed comfortable giving a forecast.
The rain is not hard. The yellow is where the rain is medium. My name is Joel. If you want to learn more about the weather, just download our app. And the orange and red is where the rain is hard.
Joel already has a good sense of organization with his thoughts and communication, skills that will be useful as he grows a career one day. Now, if your child would like to become a Storm Team 9 Weather Kid, send me an email to jjackson@WNCT.com, and I'll give you all the information you need to know. For the Storm Team 9 Weather Kids, I'm Chief Meteorologist Jerry Jackson. Class dismissed. When hurricanes hit, I'm always fascinated by the way that wildlife is able to adapt before, during, and after the storm, so to speak. Now, if you enjoy being outdoors and simply observing nature, North Carolina is one of the best states in the country for sheer variety.
While fishing along the surf, there are many different species to catch. Among the most common is the Florida pompano. Despite their name, they can be found from Massachusetts all the way down to Brazil and of course along the East Coast. They get their name due to the fact their population densities are higher in the warm waters near Florida. These ocean dwellers prefer temperatures between 70 and 89 degrees. As seasons change, they migrate to stay in warmer water. During the summer, they move north, but as winter rolls around, they head south towards the equator. While in the water, Florida pompano appears to have a yellowish belly with white sides, but when removed from the water, they appear to have a greenish-blue color on top with a silver bottom. They spawn offshore between March and September, growing very fast during the early months of life. Florida pompano usually live about 3 to 4 years in the wild. They normally feed on surf clams, shrimp, and mussels. Their fast swimming capability helps them catch their prey. If you're heading to the surf to catch a fish or two, try fishing just beyond the breakers, as this is where Florida pompano can usually be caught. Natural baits such as shrimp or cut bait make excellent choices when targeting these fish. However, make sure you check the forecast before you set out, follow all the rules and regulations, and above all, be safe. In the studio, I'm meteorologist Christopher Tyndall, Storm Team 9.
Eastern North Carolina can experience everything from record heat to snowfall, tornadoes to hurricanes. But as wild as our local weather can be, it's nothing like the weather on other planets.
A nova is an outburst in a binary system, or system with two stars that closely orbit one another. In all known nova, one star in the system is a white dwarf, which is the leftover core of a star like our Sun after it runs out of fuel. Its companion will typically be either a main sequence star, a classification that includes 90% of known stars, or a large star like a red giant approaching the end of its life. In most systems that create nova, the white dwarf and the companion star orbit so closely that the white dwarf's gravity pulls material from the companion. This material swirls around the white dwarf and forms an accretion disk. Throughout this process, the white dwarf's gravity will pull material towards itself, depositing it onto its surface, which, while fluid in consistency, is extremely hot and dense. The material pulled from the atmosphere of the companion star is primarily hydrogen. Over time, that material builds up on the surface of the white dwarf. As hydrogen accumulates, it's heated by the white dwarf, and that heat builds until it eventually triggers a fusion reaction. The gas is explosively rejected from the surface of the white dwarf. Nova are on average around 200,000 times as bright as the sun, while the brightest nova can be 10 times brighter than that. Nova can even be bright enough to be seen with the unaided eye from Earth, even if the star system wasn't visible prior to the outburst. Nova can last for days, weeks, or even months. There is a variety among nova, as they can take place with different types of companion stars and can last for different amounts of time with varying levels of brightness. However, there are two main types: classical and recurrent. Both are eruptions that take place on the surface of stars, but there are a few main differences. Classical nova erupt only once within a human lifetime. These nova will likely erupt again, but it can take thousands or even millions of years for enough material to build up on the star's surface to trigger an eruption. Recurrent nova erupt, as the name suggests, more than once. A nova is recurrent if a system has at least 2 recorded outbursts. Scientists are not yet sure why some nova erupt more frequently, but it could be influenced by the number of factors, including the type of companion star, as well as how fast the white dwarf can accumulate material pulled from the companion star. You may have heard of a supernova before, but this explosive phenomenon is different from a nova. While there are multiple types, in general, a supernova is an explosive outburst that essentially destroys the star. When a nova occurs, a large outburst takes place, but the star and the system aren't destroyed. In a core collapse supernova, a massive star collapses in on itself and creates a shock wave that produces a bright flash of light. In another class called Type LA, a white dwarf gains so much material from a companion that it exceeds the mass limit for white dwarfs, resulting in a massive thermonuclear explosion. Novas always take place in binary systems. stars. Supernovas can take place in binary systems or systems with singular stars. Also, a supernova results in an explosion much brighter than a nova. While novas can be hundreds of thousands of times as bright as the sun, a supernova can be billions of times as bright.
And that does it for another edition of Weather or Not. It's been a packed show this week with trips across eastern North Carolina, seasonal treats, some quick history lessons, some fun and games along the way. And remember, a fresh episode drops every week. Our job is simple: to keep you informed, enlightened, and a little happier too. I'm Storm Team 9 Chief Meteorologist Jerry Jackson, and this is Weather or Not.